All right, welcome back to Science with Surback. Starting to see a lot of subscribers on YouTube. That's what I like to see. We today are going to start talking about section 12.3, and section 12.3 deals with Newton's third law. So before we get into details with these notes, I just want to go over the objectives of this section. 1, you should be able to determine what happens when an object exerts a force on another object. 2, you should be able to calculate the momentum of an object. And 3, you should be able to determine what the total momentum after objects collide is. So let's go ahead and get started with Newton's third law. So Newton's third law is going to state that for every action, there is an equal and opposite reaction. All right, so a couple of key things here. Equal and opposite reaction. So we are going to talk about, with Newton's third law, one object hitting another object. So the first example is going to be kicking a soccer ball. So we're going to start out here with a little stick figure, and this person is going to run up to the ball, and they are going to swing their leg, and they're going to kick it and or exert a force. And as they kick this ball with their foot, it's going to fly in the air and eventually come and roll to a stop. So, number one, what happened here is the ball was kicked by a person. So what that person did was that they exerted a force onto the ball. Now, as that force is exerted onto the ball begins to move forward. So, just because the ball moved forward does not mean there wasn't an equal and opposite force onto that person's foot. There was. And so as the ball is kicked and moves forward, there is an equal and opposite force from the ball back towards that person. And so I'm going to represent that with an arrow. So this backwards arrow here represents that ball exerts an equal and opposite force back onto that person's foot. Okay, so we'll get into the details here about how the ball moves forward here in a second. But let's move to another concrete example here. This is somebody pushing up against a brick wall. So let's say we have yet again another person, and we have this wall, and I'm going to draw an arrow. And this arrow, what I'm going to do here is that it is going to represent that this person is pushing up against that wall. Now, at the same time, the wall is going to be pushing back onto that person with an equal and opposite force. Now, the question that comes to my mind after thinking about Newton's law and going through these examples is this. Okay, if a force is equal and opposite, why does one object seem to not accelerate compared to another object? So let's take the soccer ball example. The force that person kicked the ball with was the same force that the ball exerted back on the person. So why did the ball go flying forward, but the person stayed relatively the same? Well, the answer to that is going to be in mass. But before we get into that, let's go through, or let's list another example. And this example is just going to be dropping a ball onto Earth. And let's say that we're sticking with that soccer ball example. Let's say you took a soccer ball and you brought it to the top of your head, and then you just let it go and let that ball go down to Earth's surface. So what happens as the ball strikes Earth's surface, it is going to exert a force onto Earth, and thus the Earth is going to give that equal and opposite force back onto the ball. So it's exerting an upward force that the Earth is. So why, if the forces are equal and opposite in direction, why does it seem like only the soccer ball is accelerating? Well, the answer lies in that formula that we use to calculate force. So force, from section 1, force is equal to mass times acceleration, which is just a mathematical statement for Newton's second law. And this right here, the M for mass is going to matter. So I'm just going to put that out here. Mass is going to matter. Now, if you think about it, the mass of the Earth versus the mass of the soccer ball, there is a significant difference in those two masses, and this is why when that Earth gives that force back onto the soccer ball, it does accelerate, but it's so minute, it's so small that we barely even notice it, or we probably don't even notice it. So, again, Earth has a huge mass compared to that of a soccer ball. As a result, because we have to factor in mass into the equal and opposite forces formula, the Earth is going to accelerate very little compared to the acceleration that the ball experienced as it was dropped to Earth's surface. So the big reason here that we don't see equal accelerations is because mass matters. It's equal force, not equal acceleration. All right, so we've hammered in Newton's first law pretty well. Let's go ahead, let's shift gears to the concept of momentum and conservation of momentum. So momentum is going to be defined as the quantity of the product of mass and velocity. All right, so really all that is saying in this definition is a fancy way for another math formula that we have in this chapter. So the formula for momentum is listed as this: P equals M times V. Now, the P is going to be our value for momentum, and it is in units of kilograms times meter per second. The M is the mass, and the mass must be in kilograms, and then the V is going to be the velocity of that particular object, and that is going to be in meters per second. So let's think about momentum in terms of a driver's ed example. I'm sure Mr. Claudney in his class, he's talked about, hey, cars and trucks and anything that you drive is going to have some type of momentum. It's going to have a forward momentum, and that is what that not necessarily causes accidents, but it's something that affects accidents. So let's think about this here. Mr. Claudney, I'm sure he said, hey, be careful around big trucks, because if you're driving a little car like a lot of you do, a big truck like a semi-trailer is going to be dangerous because it's so big. Well, let's think about this in terms of a real life example. So what I'm going to do, I'm going to pause the video, and then I'm going to get a couple objects to emphasize this driver education point. All right, so what I have are two objects here. One, I have this really big cart. It's pretty heavy, or it has a lot greater mass in comparison to this little Matchbox car. You've probably seen it in class. And so what I want to do here is just represent a head-on collision between this little car and this big object. Now, to emphasize that this object here has more mass, what I'm going to do is I'm going to add a 250 gram weight onto that object. So what I want to show you here is this. I'm going to just gently tap the cars forward so that they run into one another, and I want to show you what those dangers are, or what the driver's ed is trying to teach you about the dangers of bigger vehicles. So again, I'm just going to slightly tap these things and almost say equal force, and I want you to see what happens here. Let's do that again. Didn't get a very good tap on the red car here. All right, so I didn't affect that, or I didn't touch it after those two objects move forward, and I gave them each an equal tap. Now, what you can see happen was that this big vehicle, or this big massed object, when it ran into a really small massed object, it kept plowing through, and that's because this thing right here is going to have a greater momentum, and that thing with the greater momentum is going to have that greater impact. And as you can see from this example, it drove the little car backwards. So they both were traveling at each other, and then by the end of it, you saw that the white car and the red car were moving in both the same direction, which was the direction of my finger. All right, so let's get back to notes and let's talk and explain what happened there, and then we'll keep moving. All right, so back to notes. What happened here? I'm just going to actually explain in words what we saw here with the red vehicle and the little white Matchbox car. All right, so again, put some words into what we just did. The car, the red car, had a lot bigger mass, and because those cars were traveling relatively the same acceleration and relatively the same velocity, when that red car hit the white car, because of that greater momentum, you saw it drive that white car backwards. And that's what would happen in real life if a vehicle hit in a head-on collision with a much, much bigger vehicle traveling at the same speed. Okay, so let's go through an example here, and then we have one more point to talk about at the end. So our momentum example here, we want to calculate the momentum of a 6-kilogram bowling ball that's traveling down the alley at 10 meters per second. So our formula, what we just learned is that P equals M times V. And so our P stands for momentum. It says right here, hey, we need to calculate the momentum. So this is going to be our question mark. Our M for mass is going to be the mass of that object. In this case, it's going to be a 6-kilogram bowling ball. And then the velocity is going to be that speed of that particular object, which in our example here is 10 meters per second. So we just put that back into our equation, and we take 6 kilograms times 10 meters per second. And so to show you how to do this here, if we turn the calculator on, all I'm going to do is I'm going to take 6 times 10, I'm going to press enter, and I get a value of 60. So the momentum in this case here is 60 kilogram times meter per second, and that becomes the momentum of that particular bowling ball. So the last thing that we need to talk about is conservation of momentum. And we kind of saw it in the cart example, is that, hey, the total overall momentum in a particular system, so like the car wreck I just showed you, must be conserved. Got a little misspelling here on conserve. But when we think about conservation of momentum, the easiest way to think about this, or the best example, is bumper cars. So our example here is going to be bumper cars. So if you're ever at a fair, or you ever go to a place with bumper cars, when you get in that car and you try to drive into the side of your buddy who's relatively the same size, same mass, what's going to happen here? If you're relatively the same size and you're traveling at roughly the same speed, once you hit each other in those bumper cars, what's going to happen is both of you are going to move backwards, but overall the momentum has to be conserved. To show you that here, I'm going to bring out another one of those cars here, and we'll end notes with example. So let me get those out and we'll get started here. All right, so I have now one blue car with that mass, and it's the same type of car as that red car we had out earlier. And so what I'm going to do is I'm just going to place these relatively equal distance apart, and then I'm just going to tap equally the back ends of these carts, and we're going to watch what happens. All right, so one more time, and then we'll talk about this and be done with notes. So again, relatively equal tapping, maybe. Again, equal tapping here, and perfect. All right, so you saw both of those things slide off to the, or slide away from the view of the camera, and they're moving at relatively the same speed. And that shows you here that when two objects with the same mass and relatively the same acceleration, or relatively the same speed, hit each other, they're going to move backwards and in opposite directions, but ultimately the total overall momentum from both of these cars is the same. So I hope you've enjoyed section 3, and don't forget to like this video, and as always, subscribe.